Okay, good morning, everyone. Today we are very happy to have Professor Jomaas from National Building and Civil Engineering Institute from Slovenia for a lecture at the Stakey Laboratory of Science. So firstly, I would like to give a brief introduction to Professor Jomaas. Professor Jomaas is the ERA chair holder and head of the Department for Fire Safety, Sustainable Built Environment at the Slovenia National Building and Civil Engineering Institute in Slovenia. He is an award-winning mentor, educator, and communicator. He advises ESA and NASA on spacecraft fire safety and government's research agency and companies on achieving fire safety in sustainability-driven society. He has a bachelor degree in fire protection engineering from the University of Maryland and a master degree and a PhD degree in mechanical and aerospace engineering from Princeton University. So the topic of his PhD was flame propagation and the stability of premixed flames at standard and high pressures. He was an assistant and associate professor in the Department of Civil Engineering at the Technical University of Denmark and the BRE chair and a professor of fire safety engineering at the University of Edinburgh. Currently, in addition to his full-time job at ZAC, he has an appointment as professor at the University of Primorska in the Faculty of Mathematics, Natural Sciences, and Information Technologies. So Professor Jomaas has broad experience in experimental combustion and fire safety research, including high-pressure premixed flame research and flammability in microgravity. He has written several highly cited papers. So in the FRISSBE project, he focuses on the link between fire safety and sustainability, both from the theoretical and experimental perspective. So currently, the main experimental research topics are photovoltaics, batteries, bio-based materials, and mass timber. So today we're very happy that Professor Jomaas will give us a lecture entitled "The Fire Safety Research Needs for a Sustainable Built Environment." Let's welcome. Please.
Thank you. So thank you for having me here. I will. You see, which one is the change here? This one. So for having me again, because it's an honor to be here. But I was here in 2013, as you can read better than me. I found this script from the talk I gave here on spacecraft fire safety, and as I told my hosts here, and that it was a bit different time, because this was just when the State Key Fire Laboratory had gotten to know that they were going to have the expansion, and everybody was pointing towards basically the area where this building is, that's where the new building was going to be. So just a little bit about me to put context. This is from the view from where I grew up. This is from Norway. I'm the view from my parents' house in southern Norway. I have worked and lived in 8 countries. So I studied in the United States at the University of Maryland, as he said. Did a PhD in mechanical and aerospace engineering from Princeton University with Professor C.K. Law as my supervisor. At Maryland, I worked for Jose Torrero in the laboratory. Then I did a postdoc at École Centrale in Paris with Sebastian Candel on flame dynamics, combustion instabilities. I wasn't there very long because I got a faculty position at DTU in Copenhagen. where I was for 7 years. With a short, I did a sabbatical and went to University of Queensland for 8 months. And then I was a professor at the University of Edinburgh in 2016. And now, since 2021, I've been the ERA chair for the Frisbee project. And just to give you a little bit of context, the Frisbee project is not a research project. It is a capacity building and widening project. So the goal is to collaborate, is to enhance the skills of people, with a focus not on photovoltaics, not on mass timber, not on a specific topic, but in general to create people to be better scientists, to be better at applying for funding, carrying out research, writing papers, disseminating. So I'm leading the team there. So as you can see, for the project, it's a 5-year project. And I started just at the end of 2021, and they will run until 2026. And it's almost like what they call, seed venture capital. So the goal is that the European Union gave money for us then to be self-sustained afterwards. So we build up a group, and then with 5 years of funding, we should be able to create our own funding and our own opportunities. So you can see that different from regular research projects, they're not, you can see here the focus is on capacity building. And here testing out the concept is actually the research. But again, a lot of the focus is on how you do research, how you manage this, how we can build up a structure, what's the right structure of even a balance between technicians and researchers and so on. So that's a lot of it goes also for us to increase the level of ZAG, the whole institute. So ZAG is 270 people. The fire group or the fire is about 30 people altogether. But so we write a lot about how we hire, how can we do a better hiring process, how to in better capacity building. Everyone in the group has to write plans for what they're going to do in the next year, in the next 5 years, with clear goals for what to achieve. So again, here's the fire laboratory, which was built by chance at the same time as I started. So this was open in 2022. And part of what we want to do there is collaborate. I thought I had another photo of this, but part of in the project is important is the collaboration. So you can see this visit here comes out of a result that's that we had a visit last year, and from these two people from State K that you are who are. So we had meetings and discussed things. They had been to the Combustion Institute meeting in Milan, and here you also meet Ulysses, who was then here last fall and gave a talk, and he came after the Asia Pacific conference, and I believe Ulysses is coming back also in October for further research visit. We also have other research going on with USDC, with Yu Wang, where he has a project with the University of Trieste, which is, I live actually in Trieste. It's just 45 minutes from the laboratory. And I was invited to, when they had a workshop for the Three Fires project, that Yvonne was here, and there's Chiara Bedon, who is the leader for that project there. But so we are now a part of it because they don't have a laboratory. So we're setting up, and these days planning to do some testing, working with you and with Chiara on this project. And then, of course, further to that, both ZAG and USDC has been for a longer time, but we also have become an associated partner of the IMFSC program. So we host master students for thesis. We also host summer interns in our lab through this, and have an international collaboration. And And of course, we were always welcome to host PhD students for shorter or longer periods to come and do research in our laboratory. But we are very, very proud of being part of this as well. And we are in a unique position because we're not a university, but it's because of our, say, central position in the research we do. It was agreed at the board that we could be part of it. And on that note, I just want to also do a little pitch before I go. I know some of you will be coming to Slovenia for the European Symposium on Fire Safety Science, the 5th one. Last year was in Barcelona, and this year we're hosting it in Ljubljana. And we'll also have a pre-day event where we, in the laboratory, will show some experiments, but also have talks by Professor Bart Merci and Jose Torrero. Will give to young researchers advice on publishing, building a research career. So that's advised for those that come to go to that. So that was just to give you a little bit of context of the Frisbee project and where I come from. So the talk I gave today is Fire Safety Research Needs for a Sustainable Built Environment. And do anyone know what this is?
London.
London 1666,
yes.
The Great Fire of London. So this is not a photo, but a painting this, showing this, how you had a conflagration in London based on, because of the large amount of timber used in buildings. And then, let me see here with the sound. So now that led to a ban of combustible materials, but now because of sustainability drivers, let me see if it's too loud. Then fire, mass timber is becoming very much used again. So this is from experiments done in Trondheim at the Rice Fire Research Laboratory there, where a PhD student were doing this large test. And this room, I think it's almost 20 meters. And when they did a fuel load both on the floor level and then on the ceiling level, and the walls are fully compartmentalized with wood, at some point it took they started the fire on one end, and it took about 5 seconds to sort of flash over and travel the 20 meters. So this, of course, is very difficult for firefighters, and different than what we expect in a compartment fire. So basically what we have is that, say, if we start at a big fire in London, then we created new laws. We had new laws for fire safety, had regulations, we learned many things for, now 350 years. But then in the 60s came requirements, demands for energy efficiency. It was a fuel crisis. So then new materials, plastic materials entering buildings. So then we get we have a need for regulations. And then, of course, we had the big fire in 2017 related to Grenfell that came as a result of this energy renovation. And now what we see and with sustainability is that the drivers are so quick that we have to do things on a year basis. Here we did on decades for fire safety, then tens of years for energy renovation, and now with sustainability, things are going so fast. So, and if with, say, fire safety regulation, they may take 5 to 10 years to implement, whereas the problems are introduced on a yearly level or even faster than that. So that creates a big problem. And if we want to be sustainable, then a definition of this from 1987, which actually from a former Prime Minister of Norway, Gro Harlem Brundtland, who in a commission that they had for the United Nations, they said that sustainability consists of fulfilling the needs of current generations without compromising the needs of future generations, while ensuring balance between economic growth environmental care, and social well-being. So it's not just one aspect you have to look at. You have to look at 3 aspects when it comes to this. And when it comes to fire safety, you could think that you then have maybe 3 options. One is to build a building as sustainable as possible and then add fire safety measures, which is actually often what is done because the sustainability drivers are so strong on a political level. Option 2 is the fire safety solutions that are sustainable as possible. We see this now with water mist versus sprinklers, that there's, which one is more sustainable, which ones should be chosen for this, what kind of options should you choose for your building. But in my view, the ideal goal is obviously an optimized holistic sustainability design, and this requires research. We need to, because then there's many complex factors that go together that need to be understood how to build this combined. And then, of course, just to remind you, this again is something that happens many places. This was in Valencia last year, where people think that we had Grenfell and then we learn and we know, but then you had a fire in Valencia that if you follow the timeline, in just about half an hour, not only spread to the whole building, but also ignited a neighboring building in that short time frame. So the problems are here, they're here now, and they're everywhere. So I put some slides for here. This is making an analogy between fire science and maybe AI. Because 50% of AI researchers believe that there's a 10% or greater chance that humans go extinct from our inability to control AI. We are boarding that plane rapidly. Would you get on that plane? And I make the analogy that we're making these sustainability drivers, we're forcing the politics are such that everything should be sustainable, but we're forgetting safety science in the midst of it. So basically, the fire safety research has become essential, for Europe, for the world, to reach the goals set forward with respect to energy, climate, transport, and sustainability. And innovation leads to risk. This is normal. But at some point, this risk then becomes too big, and intervention is needed. And this is now. So we need to ensure that innovative solutions are safe. Performance-based design is a necessity because prescriptive solutions are not created with sustainability in mind. So we need data, we need competence, and we need combined to use them to make informed decisions to reduce fire risk. So informed decision based on true facts and research. And to show, that this is throughout, I borrowed this slide with the permission from Wojciech. So I kept his ITB logo. He gave this talk just a few weeks ago in Zurich. And he shows that, that if you look at a built environment, the fire safety research needs are everywhere. Whether it's energy generation, distribution, and storage, whether it's 3D printing of buildings, ventilated and green facade system, electromobility, infrastructure, future mass transit, mass timber, and decarbonization. It's in the entire built environment that we have new innovative solutions that are being brought forward at a pace that it's difficult for safety to be included at the same time. So I could have talked, about many other things, mass timber, bio-based materials and facades as well. But to go a little bit more in depth, I focus here on batteries in terms of EV and e-mobility, and also then on PV modules on roofs. So when it comes to batteries, or actually both of them, it's kind of similar. You want to know about the ignition, you want to know about the fire dynamics, you want to know about how it interacts with the structure or the compartmentation, and you will need to take into account the firefighting. And of course, from a sustainability point of view, you need to know that this also what the environmental impact is on all of this. And in terms of batteries, e-mobility, the problem is bigger on the smaller level than it's on electric vehicles, because you also have a proximity to people. The speed with which you reach 1 megawatt fire, say a flashover, a completely inclusion of the building, is very fast, and it's very unpredictable, because it can be many things, like cooking. Cooking fires is one of the main causes of fire, but it happens when somebody doing, or well, people can fall asleep and so on. But with the battery fires, it can very often happen when people are sleeping, not expecting it. It's not active. The device is not technically seen to be active. So if you look at some of the research that's been done for batteries, like a e-scooter, you can see that it can reach 1 megawatt in less than a minute. And if you know, like from classic fire science, an ultra-fast fire takes 75 seconds to reach 1 megawatt. That's based on a liquid pool, that's based on an arson scenario. So these fires reach that size even faster than a liquid fuel. But not only that, there's also very fast development of, for example, hydrogen fluoride, which here we did. These are some tests we did in our laboratory, that you could get values that are 10 times lethal in a very, very short time. And I think this was the case, for example, in the battery factory fire in Korea, where 23 people lost their lives. They went to fight the fire. They thought they were going to approach it, and then because of the toxicity, were succumbed to the fire. People need to, so there's a need for also education is for people knowing that they need to just leave instead of trying to fight the fires. There's been in New York and in Vancouver, it was the leading cause of death in the past years. Now they've make several regulations to improve that, but very important problem. So in terms of sustainability, we often have, a very nice utopia. So no matter how good of a utopia you create, your dystopia is bad enough, it does not matter. So this is from a bus fire in Paris, an electric bus. And because of this, and the same in London, because of the fires that they experience, then they lead to a ban. So you do all the development, and then you have one fire, and you end up maybe with a ban, and it's all the buses, all the hundreds of buses of the electrical fleet are then just put in a parking lot. And that's not an informed decision. That is just what they refer to as a knee-jerk reaction, that people say, oh, we don't know what to do with it, so we just put it away. We don't want to deal with it. We don't allow it. And that's not a good solution either. So in terms of car parks, I think, for electrical vehicles, the most interesting part will be obviously in car parks, because a car fire on the street is, well, often, most often people are able to get out. If it's involved in a crash, it could be different. But in general, if a car is in the open, people can go out of the vehicle and it can burn out. But in a car park, we've seen over the last few years, many car parks have collapsed. And this is a combination of wanting to build leaner buildings. And it's not related to EV. The biggest problem is actually the size of the cars. So this, you can see in the EU, the average width of new cars has now surpassed 180 centimeters, which is often used as a lower threshold for on-street parking in Europe. And if you put it in a parking garage, also the size, that now, if a parking was designed for something like this, you see that the other cars fill it, and you have the cars being much closer, which leads to a bigger fire. So it was often in research. This is research done in Europe in the 90s, and this was what they perceived as an open car park, and they had 3 cars. And it was always assumed that you would only have 3 cars burning as the fire scenario. That's the design fire. But now we see that, and you can see here it's open, it's right on the edge. If you look at the fire, most of the energy is actually here, or a lot of the energy is going outside of the car park, not staying inside. So the microphone. And then we end up with something like this, which was the Luton Airport in outside of London, where you can see a car was so big that the deck went. And if you think from a firefighter perspective, that the car coming through the deck, it may look like they could enter the building, but the fire, they had to fight it from the outside. And the aftermath, it looked like this. And this was a car. This was starting in a car. It was not an EV. It was starting in a car. And the driver drove into the car park. And he didn't realize, I've said, there were CCTV cameras showing that there was smoke coming from his wheel, from the engine. And he was in a rush. And so he was driving, and he parked. And he didn't even park next to other cars. He parked actually in the driving lane. And he tried to use 2 fire extinguishers to extinguish it. Didn't manage. And even in a place where they can inform people, cell phones, people call the fire service, it was brought down the entire structure. The fire service could not get in. By the time the fire service got in there was even cracking in some of the, you could saw from the body cam of the firefighters, they were walking in the stairwells and they were cracking in the walls already. So they withdrew, and rightly so, because it led to a collapse and hundreds, if not 1,000 cars being involved. What is particular for EV though is that you have the vapor cloud explosion, and you have an ignition with a jet-like base under, which will lead to a fire going to other cars. And many people are saying that, well, if the gas tank were to burn, it will also lead to that. But the gas tank is not as easily involved in a fire, or as often involved in a fire, as the battery is in an electric vehicle. So there are new challenges, but the main part is that they're, when the cars are parked very close by, they can ignite each other. And of course, the other part is that cars these days are predominantly plastic outside instead of a metal. But so what's, for in terms of the metal in the vapor explosion, this is some firefighters in Belgium. They're putting out a fire. I like the guy with the umbrella. He's having a watch of what's happening. And then that's the roof of the car that blew up. So they didn't expect it. It comes completely unexpected to them, that is explosion. They would, if they were expecting an explosion, they wouldn't be standing with their face basically inside the car. So another aspect that's been pointed out is that in order to cool down an EV fire, you need to maybe use as much as 25 times as much water. And then you had a water runoff and so on for environmental damage. So the key here is that there's some new challenges. They're not necessarily larger, but they're different. So we need to understand them, we need to research them, we need to inform the firefighters, we need to work on the technology and get different stakeholders involved. And then, of course, you have things like this. Now so some of the research is related to electric fires, is with fire blankets. And just recently, the Fire Research Safety Research Institute from UL issued that that the firefighters need to be very careful when using a fire blanket, because you can accumulate gases and you can have explosion afterwards. And I know from tests like this, that's sort of promotional video, is that so lifting of blanket will introduce oxygen and may cause a backdraft. So they say they've included this. It's not shown in the video, but obviously they must have done some experiments where this actually happened. They don't want to show it, but this, they probably in some experiments that they did also at in Singapore, that they saw the same as UL saw in their research. And the challenge with this is that often the identification of the problem is missing. So you will end up, when there's many new problems, there will be also many what is referred to as a solution looking for a problem. So people haven't understood the problem, because what, to me at least, the challenge with this, yes, it may work, you can fill it up and you can fill the car, but how are you going to have that for every car in this, or in the parking garage? Or if some people say, oh, we can move it to the car that's burning. But keep in mind that in London, in Stavanger, in Liverpool, the problem wasn't the firefighters couldn't get to the fire even with the hose. So how are they going to get to the fire with this? If they could get there with a hose, they would do so. But in those fires, they didn't get there in time for that. So we need a better solution. And then also say with fire blankets, people say, oh, well, then the people can do this. But should we expect the regular citizen to be the firefighters? I don't think so. This is also having talked about the toxicity and the problems that we can have. It's important to acknowledge that it's better to leave it for the firefighters, but also to come up with solutions that don't have to involve citizens and rather keep them safe. So the second part that I'm going to talk about is about photovoltaics. And in Europe, they have something called REPower EU as part of the European Building Performance Energy Performance Building Directive, and there's gonna be by 2030 more or less PV on all buildings on the roofs. And what I like to emphasize is that all buildings means hospitals, it means nursing homes, it means museums, it means timber buildings. And particularly telling for this one, this is a proposed museum in Lund, is that you also see that now you have people interacting with the roof. And for anyone studied some fire science, they know that the biggest problem for fire is the humans making mistakes. Maybe some people will walk on it. There will be more trash accumulated. It's a system that is meant for no human interaction, and then you get that. So what are we looking at? Well, so this is a fire that happened last year at a distribution center. This is ideal. The size of this is about 8 football fields, the roof. So even though it looks like it doesn't cover the whole roof, this fire resulted in 500 to 600 panels being involved in the fire. However, I didn't show this, but this was a new build, and it managed to survive the fire. Other buildings have not been as well protected, so you need to know the solution both for separation distances, but also for what kind of materials you're going to use. So I'll show. So we at SAG we created a fire safety guideline for building applied photovoltaic systems on flat roofs. And we're working now with the group here at UST to make also a translation into Chinese, because we find that it's important to share this sort of basic knowledge information with everyone. It's not an installation guide, it's practical, common sense things that people should be aware of. And similar, as I said, as I showed with the batteries, you know, we look at the ignitions, fire dynamics, the roof construction, and then fire safety operation or firefighting operations. And the goal is to avoid large consequences of a PV fire on roof, and that could be by minimizing ignition frequency and power, or minimize the fire spread rate and extent. So this is component and product level, and there's a lot of codes and regulations and tests for components, for the PV, for the cables, for the photovoltaic panel itself, but very little or nothing on the system when you put it on the roof, which is the real problem. Because we test the roof and we approve the roof without photovoltaics, and then when we put the photovoltaics on the roof, it changes the fire dynamics, and the fire can spread, it become bigger. In terms of the fire, we can look at two main scenarios. It could be a fire that spreads on the roof, and then we want to protect it from coming to the building. And we can also, so the fire dynamics, but also looking at the roof construction, what we need to protect it. And there can be also problems with fires starting inside the building involving photovoltaics. This is from a fire in Norway. It led to initial 20 million euros loss, but now it's more than double of that, because they needed to change all of their distribution logistics for all of Norway, Sweden, Denmark, based on this fire. This fire started in a truck charging inside the building. It went up and to the roof, and because nobody thought that the fire, you know, was spread on the roof, because if you have a regular roof without photovoltaics, the energy would just go up and it would go outside. But with the photovoltaics, now it's spread laterally, and it spread so that it involved two sections. So they didn't have a parapet, they didn't have the fire break to go above the roof level. So they ended up with a very, very big fire, 9,000 square meter damage. They needed to use wildfire type of helicopters with big pods of water to extinguish it. So it was also concerns of the environmental damage with the leakage of contaminated water to streams and nearby areas. And is it a problem? People often ask, and I ask also Yu Wang and some of the students when it comes to BIPV, because for full BAPV, we have some numbers that there are, say, maybe expected something like 29 fires per gigawatt. For the conference in Slovenia, my PhD student looked in Italy and Slovenia very closer, and the numbers are pretty much the same. In Slovenia, actually almost 40 for the last 2 years. So it does happen quite regularly. Of course, not all of these fires become big, but that's what we want to. It's okay, you know, we can't prevent somebody from dropping a match or some electrical fault to happen, but we want it not to necessarily make it to the news. We don't need a big fire. So the problem is that it changes the fire dynamics, and this is some work by a former PhD student, Jens Stemmer Christensen, who's now at DBI in Denmark. And the point is, so he did the work. Here, there's just a PMMA plate. There's nothing above it. So it burns like this. So take a note, this is 20 minutes. And then it's 50, 80. So it's just regular flame spread. But then we put not even a photovoltaic panel on top, just a metal plate. We did also with a photovoltaic, and the results are pretty much the same. And 15 centimeters above it, 10 minutes, and this is 20 minutes. Remember 20 minutes, the flame was just about this size, but just here. Now it's spread, and you can see it consumed all of the materials and a much bigger fire that will then very easily spread to other places. So the basic thing, the basic premise for most roof construction is that if you have a fire, it will just burn like this, and you have some flame retardants in the membrane, and you have a type of insulation that has been tested for this type of scenario. And then, but when we put the photovoltaics, we change that and we get the flame spread. So in our lab, we've done quite a lot of testing. We also done testing with arcing. So because some people say, oh, well, you use a wood crib. Why you use a wood crib? Well, we use a wood crib because it's more repeatable, and it actually just captures the fire at a slightly later stage than the arcing. We've also done testing with, just to show that the geometry. So if you have upward panels, it's like you don't have any panels, so it doesn't influence the fire spread. But then we have here with panels, and we get then the same crib here leads to a bigger fire that will look maybe something like this after 10-15 minutes. So this, even with something like 4 panels, this is 4 by 4 meters, so we're burning maybe 12, 14, not even, so this maybe is on 10, maybe 10 square meters of roofing membrane, and this could be 2 to 3 megawatt fire, starting from a 15 kilowatt small wood crib or from arcing. So to demonstrate also the different solutions, we showed simultaneously. So this is a roof construction with just bitumen on directly on EPS. Here we have a mitigation layer. So here we have a mineral wool between, and this is a build-up with EPS, a bitumen, and then a mineral wool, and then bitumen again. And we showed the difference with the 2 different panel configurations. So a bit later, you can see this, that if you have a mitigation layer, the fire will stay local. If you don't have a mitigation layer, it can burn through and engage and burn the combustible insulation. And if you have a photovoltaic like this, it becomes quite a large fire compared to this. This was the same starting point, right? So you can clearly see that the photovoltaic is the one that enhances the flame spread, leads to the bigger consequences. In terms of firefighting operations, some of the key things are safe rooftop access. You can sometimes see that people put the photovoltaics all to the edge of the building, so then it's impossible for the firefighters to access. There's also certain sizes you want to have, so the firefighters can reach across, because they can only spray maybe 40-45 meters. So if you make it just an endless array of photovoltaics, they will not be able to reach where the fire is. And then, of course, you need to take of their safety and also what as a good fire extinguisher medium. So we've just collected from other people what sizes. So our recommendation here, this is consequence and or severity and probability. So we say that this combination of quality of products and installation, and also of the roof buildup. So some people confuse and say, oh, you recommend incompetent installer low quality components because it's also green. Well, it's lighter green. We're just saying that the probability of a fire will go up, but the consequence may not still be larger because you have built a robust roof. And then the challenge for combustible insulation is that combustible insulation is not the same. That's a wide range. It can be from a very, very flammable material to a thermoset, highly flame retardant material that may have a quite good fire performance. But it needs to, we recommend for all solutions that is tested, but what we say here, what we say not the combustible insulation, insulation is, if I go back, is what we refer to in the guideline is particularly like a setup like this with an EPS, a very flammable, lightweight insulation material. So when you invent a new technology, you uncover a new class of responsibility, and it's not always obvious what those responsibilities are. So in rounding off, so who should solve this problem? How should we solve these problems that I've been presenting? This was, by the way, from a fire in the Netherlands, where they found, I think, about 3 kilometers away, pieces of the photovoltaics. So this was not a fire in the photovoltaics as such, but they were involved, they were on the building, and they found in in fields as far as 3 kilometers away, where kids were playing, where animals were feeding, they found pieces of glass that because it was transported with the plume from this bigger fire. So I said a little bit about this before, and it's a bit complex, but we used to work from large fire events and then protect life and property, and then we have rules. But now the goal is climate change. We have an emergency that is not related to the fire. It's a different thing. And then those lead to and push very hard on objectives that we need to have building, but nowhere in here is safety really explicitly addressed. So we used to have safety as the main driver, but now there are other drivers that are going. It's human well-being, it's social, societal responsibility for the planet, and in the midst of that, we're forgetting that safety should be part of it. People always think that safety is always implicitly included, but it's not. So basically, I'm not going to go through it in large, but we need to have a combination of fire safety design, energy design, and environmental design, where we look at how this can be then optimizing the built environment. And I think this is Ulysses has created this figure. But so we need interaction between fire safety design and environmental design, between energy design and environmental design, and then fire safety design and energy design. And it needs to include property protection, life safety protection, and so on. And how do we do this? We need a wide stakeholder commitment. We need a concerted effort, so collaboration. And we need to work with each other, not for. I like that UL often say that they do research with firefighters, not for them. Because if you think that you do research for somebody, you don't necessarily understand what their problem is. So you can give them something and they're like, yeah, thank you, I can't use that for anything. So it's very important to listen to what is the actual problem of the stakeholders, so that you can make sure that you're not providing, again, a solution looking for a problem, rather than having understood the problem and then providing a solution. So we need education and training, competence requirements, dissemination of knowledge across borders, regulation guidelines, and research. And unfortunately, as Wojciech pointed out in another figure, the innovation cycle will create new challenges, so research skills are needed. So we can have a tragic fire, or we can have an innovative new technology leads to an unknown issue. We're trying to engineer the solutions. We do experimental verification, dissemination of results, widespread of a solution, and then stakeholders accept the solution and get used to it. So you see that it's both fire incidents, but also new technology that needs to be included. Now, it used to be maybe just the tragic fire that led to this, but now we also have the innovative technology that's feeding into the need for the research. And then we will put that in and solve this unknown issue. And in many cases, the knowledge is there. So I round off with this. This was the wildfire in Maui in 2023. And this house, in the midst of all of this house did not burn. And why didn't it burn? Well, the owners of this house have read like NFPA guidelines, read up on wildfire. They had made sure that they trimmed their yard. They made sure that they had safe distances. They used different materials for their facade. So they basically read up, and they were willing to invest in their own protection, because this is a private house, so it's not a public building, so they had to do it on their own. But in the end, they then ended up withstanding the fire, whereas all of their neighbors burned. I don't know whether that helps them, because whether they want to live here now with all of this around, but that's a different. So the willingness to have public awareness and social and sociable responsibility. So with that, that's me observing some experiments in the lab. I don't do much, that's the students that do. So I just came and looked at what they had been creating. And so I'll take any questions and just, again, say that we're very happy for the collaboration. We're happy to continue collaboration and welcome all of you to Slovenia.